250 buildings in southern England still have thatched roofs with base coats applied between 1300 and 1500 AD, 7 feet of accumulated straw that has kept structures dry for 7 centuries. No tar, no synthetic sealant, just overlapping geometry that channels water faster than capillary action can draw it inward. In 1212, London issued building regulations that would change urban construction across medieval Europe. The ordinance was stark. Whosoever wishes to build, let him take care that he roof not with reed, nor rush, straw, nor stubble, but with tile stone or lead. The regulation wasn't aesthetic preference, it was fire prevention. Devastating blazes had swept through London, Canterbury, Winchester, Worcester, and Chichester between 1077 and 1202, spread by thatched roofs that caught embers and became torches. But the regulation revealed something more important than fire risk. By 1212, medievals, builders had already developed multiple waterproof roofing systems that required no tar, pitch, or organic sealants. Clay tiles using the Roman imbrex and tegula system, stone slate split from quarries and laid in overlapping courses, lid sheeting for churches and important buildings, and yes, still thatch, but thatch so sophisticated that archaeobotanist John Letts discovered 250 buildings preserving base coats from the 14th through 16th centuries, 7 feet thick in places from continuous maintenance. These weren't primitive expedients waiting for modern materials to improve them. They were engineered systems exploiting principles that remain valid today. Overlapping creates redundancy, steep pitch uses gravity, proper spacing allows ventilation, and breathability prevents trapped moisture. Medieval roofers understood that waterproofing wasn't about creating impermeable barriers, but about channeling water so efficiently it never had time to penetrate. The archaeological and historical record proves these systems worked. William Harrison, writing in 1587, described English roofing. Where plenty of wood is, they cover them with tiles, otherwise with straw, sedge, or reed, except some quarry of slate be near hand. This wasn't aspirational, it was documenting reality. Medieval people had choices about roofing materials, and each choice reflected sophisticated understanding of local resources, climate conditions, and waterproofing principles. The question isn't whether medieval roofs worked without tar. Surviving 700-year-old structures prove they did. The question is, what exactly did medieval builders understand about water physics, material properties, and construction geometry that allowed them to create waterproof roofs using nothing but clay, stone, plants, and lead? Thatch seems the least likely material for waterproofing. Straw, reed, and sedge are organic fibers that absorb water. Yet properly, constructed thatched roofs shed rain as effectively as any medieval roofing system, and with maintenance, lasted as long or longer than alternatives. The key was understanding that thatch doesn't repel water. It moves water. The fundamental principle is deceptively simple. Water flowing across a surface faster than capillary action can draw it inward, never penetrates. Medieval thatchers created surfaces where water always moved downward, racing gravity toward the eaves before molecular forces could pull it into the material. This required specific angles, precise overlapping, and density control that took years to master. The pitch was critical. A thatched roof required minimum 45-degree angle, though steeper was common. At this angle, raindrops hitting the surface immediately began flowing downward rather than sitting on horizontal surfaces where they could soak in. The steep pitch also meant wind-driven rain struck at angles that reduced penetration. Modern thatch, typically, uses 50-degree pitch, continuing medieval practice validated through centuries of observation. But angle alone didn't create waterproofing. The material arrangement mattered enormously. Thatchers bundled vegetation into yelms, tight bundles of aligned stems about forearm diameter. These yelms were laid in courses starting at the eaves and working upward, each course overlapping the one below by several inches. The overlap depth varied by material and climate, ranging from 3 to 8 inches based on archaeological analysis of surviving medieval thatch. This overlapping created a shingled effect where individual straws layered like scales on a fish or feathers on a bird. Water striking one straw encountered another below it, creating continuous downward paths. Even if water penetrated the first layer, and some always did, it met another layer beneath, then another, then another. By the time water might work deep enough to reach roof structure, it had typically run off the edge. The material selection reflected sophisticated understanding of fiber properties. Water reed, harvested from wetlands, was premium material. The stems possessed natural waxy coatings that resisted absorption. Reed grew straight and uniform, making it easier to align properly. Most importantly, reed was durable. A well-maintained reed roof could last 40 to 60 years. Archaeological evidence shows medieval roofers recognized these advantages, using reed whenever available and affordable. Wheat straw served as the more common alternative. Medieval wheat varieties grew nearly 6 feet tall, producing long, strong stems with thick walls. These heritage wheats, now nearly extinct, had properties modern short-stemmed varieties lack. The long stems allowed proper overlap without requiring excessive material. The thick walls resisted crushing and maintained the air pockets that contributed to insulation. The securing method was equally important. Thatchers used hazel, spars, twisted wooden stakes split from hazel branches. These spars were driven through the thatch at angles, pinning multiple layers together while allowing flexibility. The flexibility was critical. Rigid attachment would create stress points where wind could lift sections or where thermal expansion might damage material. The spars let thatch move slightly, distributing stress across the entire surface. The base preparation mattered as much as the surface. Medieval roofs used closely spaced rafters covered with horizontal battens, thin wooden strips running perpendicular to rafters. These battens provided attachment points for thatch while creating ventilation gaps behind the weathering surface. Air circulated through these gaps, evaporating any moisture that penetrated the outer layer before it could reach interior structure. This breathability was essential. It turned inevitable minor penetration into harmless vapor rather than structural rot. The ridgeline presented the greatest challenge. Where two roof slopes met at the peak, water from both sides converged. Medieval thatchers addressed this with specialized ridge construction. They created thick, tightly packed caps using best quality materials, often water reed even on roofs otherwise thatched with straw. This ridge cap was secured with horizontal wooden liggers laid along the peak and tied down with twisted hazel bonds. The ridge required more frequent maintenance than main roof surface, typically being rebuilt every 10 to 15 years, but this localized replacement was far easier than rethatching entire roofs. The maintenance culture surrounding thatch reveals deep understanding of the material. Rather than stripping roofs completely, thatchers added new layers atop old ones in a technique called spar coating. This built up remarkable thickness over time. The 7-foot accumulations John Letts documented represent centuries of continuous care. Each new layer improved insulation and weatherproofing while distributing wear across multiple generations of material. William Harrison's 1587 description noted regional preferences. Where wood was plentiful, tiles dominated. Otherwise, thatch prevailed. This reflected economic calculation, not technological limitation. Thatch required regular skilled maintenance, but used renewable local materials. Tiles demanded expensive kilns and specialized clay, but needed minimal maintenance once installed. Medieval communities chose based on local resource availability and economic priorities. The clay tile system, medieval Europe, inherited from Rome, represented waterproofing through geometric redundancy rather than material impermeability. The imbrex and tegula design, curved tiles covering flat tiles joints, created roofs where no single failure point could cause leaks. Understanding this system reveals sophisticated grasp of how overlapping geometry defeats water penetration. The tegula was a flat rectangular tile with raised edges along its long sides. These tiles were laid in rows up the roof slope, their raised edges creating channels. The imbrex was a half-cylindrical tile, shaped like a lengthwise cut pipe section. These curved tiles were placed over the joints between tegulae, covering gaps and creating continuous water paths. The genius of this design lay in its redundancy. Water hitting the curved imbrex immediately flowed down its channel. If wind drove water under imbrex edges, it encountered tegula's raised sides, which channeled it back into main flow. Even if water penetrated past both barriers, unlikely on properly pitched roofs, it reached flat tegula surface, which directed it downslope through channels formed by adjacent tiles' raised edges. Medieval adoption wasn't uniform initially. Tile required specific clay, kiln facilities, and skilled labor, making it expensive compared to thatch. Early medieval tile production clustered around monasteries and royal estates that could afford the infrastructure. But by the 12th century, documents show clay tile use being encouraged specifically to replace thatch for fire safety. The 1212 London regulation accelerated this transition in urban areas. The manufacturing process reveals sophisticated ceramic understanding. Tileries, medieval tile factories, required clay with correct balance of plasticity and sand content. Too much clay meant tiles cracked during firing from excessive shrinkage. Too much sand made tiles porous and weak. Medieval tile makers tested clay by feel and fired small test batches before committing to full production. The tiles were formed in wooden molds, giving consistent dimensions. For tegulae, raised edges were created by placing thin wood strips along mold sides. Clay was pressed firmly into molds, then tiles released and left to dry slowly. Rushing this stage caused warping that made tiles difficult to fit on roofs. Properly dried tiles were stacked in kilns and fired for days at temperatures around 1,000 degrees Celsius. The resulting tiles possessed remarkable durability. Well-fired medieval tiles could last centuries. Archaeological excavations routinely find intact tiles at sites abandoned 600 years ago. The longevity stems from complete vitrification. Heat fuses clay particles into nearly glass-like structure that water cannot penetrate. Medieval potters couldn't measure temperatures precisely, but they understood kiln management through observation, knowing when flames shifted from red to white-hot, when tiles glowed properly, when cooling could begin. Installation technique determined whether expensive roofing material would perform as designed. Roof structure needed to support substantial weight. Clay tiles were far heavier than thatch. Medieval carpenters used closer rafter spacing and sometimes added longitudinal purlins to distribute load. Tiles were hung on wooden battens using small projecting knobs or ridges on tile backs. Later, medieval improvements included tile hooks, wooden pegs that engaged notches in tiles, allowing secure attachment without penetrating waterproof surface. The critical installation variable was overlap. Each tile row overlapped the one below by at least 3 inches, ensuring water couldn't flow backward even in driving rain. This headlap meant approximately half of each tile was covered by the one above. This redundancy provided system waterproofing. Even if individual tiles cracked, common occurrence, tile beneath remained intact, maintaining weather protection. Side overlap was equally important. Medieval tilers ensured tiles overlapped neighbors horizontally by at least 3 inches. Combined with imbrex covering joints, this created roofs where no single failure point could cause leaks. The phrase modern engineers use, belt and suspenders, captures this philosophy. Multiple backup systems ensuring function even when individual components failed. Building. Regulations from 13th century show authorities recognized tile roofing's superiority for fire prevention. The 1212 London Ordinance was followed by similar regulations in Winchester, Canterbury, and other major towns. These mandates drove tile production expansion and technical improvements as manufacturers scaled up to meet demand. The medieval tile industry developed regional variations. In eastern England, flat tiles without raised edges became common, laid in simple overlapping patterns. These pan tiles required steeper roof pitches but were easier to manufacture. In western regions closer to Roman influence, the imbrex and tegula system persisted. Regional clay deposits also affected tile color. Iron-rich clays produced red tiles, while calcium-rich clays created buff or cream colors that became associated with particular regions. Standard tile size was established in 1477, 10.5 inches by 6.5 inches by ½ inch thick. This standardization improved interchangeability and simplified installation, though hand manufacture meant variation remained. The regulation also reflected growing sophistication of building codes. Recognizing that consistent dimensions improved construction efficiency. Where slate deposits existed, medieval builders gained access to roofing material combining extreme durability with natural waterproofing. Slate's geological origin: sedimentary rock compressed and heated until developing layered crystal structure, created material that could be split into thin, flat sheets, ideal for roofing. The earliest documented medieval use of slate in Britain dates to late 2nd century at Roman Fort Saguntium near Caernarfon, Wales. After the Roman period, slate quarrying declined but never disappeared entirely. Archaeological excavations in Kent and Sussex have uncovered slate roofing on medieval farmsteads and villages, not just high-status buildings as once assumed. The appeal of slate was straightforward. It was effectively permanent. A properly installed slate roof could last 200 years or more. Unlike organic materials, slate didn't rot. Unlike clay tiles, it didn't crack from frost. Its low water absorption rate, typically below 0.4%, meant water couldn't penetrate and cause damage through freeze-thaw cycles. But permanence came at significant cost. Slate had to be quarried, labor-intensive process requiring specialized knowledge. Medieval quarrymen looked for rock beds with consistent grain orientation, indicating slate would split cleanly. They extracted large blocks using iron wedges and hammers, then transported them to splitting sheds where skilled craftsmen divided blocks into roofing slates. The splitting process was critical skill. Master slate splitters could read stone's grain structure, knowing exactly where to place chisels and how hard to strike to achieve clean splits. Single mistake could ruin entire blocks. Best splitters produced slates of remarkably uniform thickness, typically 3/16 to 1/4 inch thick, allowing efficient roof coverage without excessive weight. Medieval slate roofs employed same overlapping principle as thatch and tiles, but with even greater precision. Each slate overlapped the one below by at least 3 inches at top, dimension called headlap. This meant each point on roof was covered by at least 2 layers of slate, and most areas were covered by 3. Water flowing down roof encountered slate at every point, never finding bare underlayment or rafters. The installation technique reveals sophisticated understanding of material behavior. Slates were attached using copper or iron nails driven through pre-punched holes near slate's top edge. Holes were positioned so slate below covered them, preventing water entry. Medieval slate roofers understood that nail placement affected how slates hung and moved. Holes too close to edge risked breakage, too far from edge, and slates hung at wrong angles. Most critically, medieval roofers didn't seal slates together. Modern construction often uses adhesive or sealant to create watertight joints. Medieval builders recognized this was counterproductive. Sealed joints prevented ventilation and trapped any water that did penetrate. Instead, they relied on gravity and overlapping geometry. Water flowing down slate surfaces moved too quickly to be drawn sideways through joints by capillary action, especially given slate's smooth, non-porous surface. Regional variations developed based on local geology. Welsh slate, renowned for fine grain and easy splitting, dominated British markets. Once medieval trade networks made transportation economically viable. Cornish slate, harder to split, offered distinctive colors ranging from gray-green to blue-black. Scottish slate, quarried in highland regions, tended toward thicker, heavier profiles, but possessed extreme durability in harsh northern climates. The expense of slate meant it appeared primarily on high-status buildings during early medieval period. Churches, cathedrals, castles, and manor houses could justify investment. As quarrying efficiency improved and transportation networks developed, slate became more accessible. By 15th century, substantial merchants' houses in towns near quarrying regions began sporting slate roofs as status symbols. Maintenance requirements were minimal compared to thatch or even tiles. Well-installed slate roof might need no repairs for decades. When maintenance did become necessary, it usually involved replacing individual broken slates, task requiring skill but not complete re-roofing that thatched buildings needed. This long-term economy offset slate's high initial cost, making it attractive to institutional builders thinking in multi-generational timescales. The 1372 accounts from Westminster Abbey show slate being purchased from Collie Weston in Northamptonshire, documenting medieval, long-distance slate trade. These transactions reveal slate was valuable enough to justify transport costs over considerable distances, reserved for important buildings where permanence justified expense. Lid sheeting represented medieval roofing's premium option, offering complete waterproofing combined with remarkable durability. The material's unique properties, malleability, allowing complex shaping, resistance to corrosion, and effective impermeability, made it ideal for situations where other materials couldn't perform adequately. Medieval lead production followed techniques refined over centuries. Lid ore was mined, crushed, and smelted in furnaces, producing ingots that were then cast into sheets. The casting process required considerable skill, maintaining correct temperature, creating uniform thickness, and handling toxic fumes safely. Once cast, sheets could be worked cold, making lead unusually versatile for roofing applications. The primary use for lead roofing was on churches and cathedrals, where its expense could be justified by building importance and where its properties solved specific problems. Flat or low-pitched roofs that wouldn't shed water quickly enough for tiles or slate could be covered with lead sheeting, providing complete waterproofing regardless of pitch. Complex roof geometries with valleys, dormers, and penetrations could be detailed with lead-formed and soldered to create continuous barriers. The installation technique exploited lead's malleability. Sheets were laid over wooden substrates with joints overlapped and dressed, carefully folded to create mechanical locks. Medieval roofers understood that soldered joints, while creating perfect seals, didn't accommodate thermal expansion well. Lead expands and contracts significantly with temperature changes. Rigid solder joints could crack under this movement. Instead, dressed joints allowed controlled movement while maintaining weather tightness through mechanical overlaps. Flashings, lead pieces sealing junctions between roofs and walls or around chimneys, demonstrated medieval understanding of how water behaved around obstacles. Rather than trying to seal directly to masonry, which cracked as materials moved differentially, medieval builders embedded lead into mortar joints during construction. The lead could flex slightly as masonry settled and temperature changed, maintaining seal without catastrophic failure. The weight of lead required robust roof structure, typically heavy timber framing. But this weight also provided advantage. Lead roofs resisted wind-up lift that could damage lighter materials. In exposed locations, particularly on tall buildings, lead's mass contributed to stability. Lead's longevity is remarkable. Medieval lead roofing, surviving on cathedrals and churches, often dates to original construction. 600-year-old lead remains functional, testament to material's resistance to corrosion. The oxidized surface layer that forms, lead carbonate, actually protects underlying metal, creating self-renewing barrier that prevents further degradation. The cost limited lead's use to important buildings and specific applications. A typical medieval house couldn't justify lead roofing expense, but for churches, monasteries, castles, and royal buildings, lead provided waterproofing that required minimal maintenance and lasted indefinitely. The investment was justified by building importance and expectation of centuries-long service. Medieval building accounts document lead purchases and installation. Significant quantities of lead appear in records for cathedral construction and repair. These documents reveal lead was valued enough that theft was a serious problem. Lead stripped from church roofs became ongoing concern, requiring guards and severe penalties. Regardless of material choice, medieval waterproof roofs shared common principles reflecting deep understanding of how water behaves and how construction, geometry can exploit that behavior. These principles transcend specific materials, explaining why diverse approaches all achieved similar results. The first principle was pitch, roof angle. Steeper roofs shed water more efficiently. Thatch required minimum 45-degree pitches. Tiles allowed 35 to 40 degrees. Slate permitted even lower angles, sometimes 25 degrees on large institutional buildings, though steeper remained preferable. Medieval builders understood that pitch determined how quickly water moved, which determined whether it had time to penetrate. But pitch alone didn't create waterproofing. The roof had to direct water away from vulnerable points, ridges, valleys, edges. Medieval carpenters designed roof geometry to minimize problem areas. Simple gable roofs with single ridgelines were preferred for vernacular buildings because they had fewest weak points. More complex structures with multiple roof planes required careful attention to valleys, where water from different slopes converged. Valley construction varied by roofing material. Thatched roofs typically swept thatch continuously through valleys, creating smooth transitions where materials from both slopes intermeshed. Tile and slate roofs required different approaches. Medieval builders used lead sheeting in valleys on high-status buildings, creating waterproof troughs that channeled water efficiently. On simpler structures, they might use specially cut tiles or slates arranged in overlapping patterns mimicking lead's function. Eave design was equally critical. Eaves, where roof overhangs wall, had to accomplish multiple functions. They needed to protect walls from rain, direct water away from foundations, and prevent wind from lifting roofing materials. Medieval builders achieved this through generous overhangs, typically extending roof 12 to 18 inches beyond wall face. Gutters, in modern sense, were uncommon on vernacular medieval buildings. Instead, roofs simply shed water to ground, where soil drainage or paving directed it away from foundations. Larger buildings, particularly monasteries and cathedrals, did employ gutters carved from stone or formed from lead. These channeled water to downspouts at building corners, preventing erosion and foundation damage that unrestricted water flow could cause. The relationship between roof and walls reveals sophisticated understanding of moisture management. Medieval timber-framed buildings typically elevated wooden sills above ground level on stone foundations. This prevented ground moisture from wicking into structural timber. The roof's generous eaves kept rain from reaching wall foundation junction, most vulnerable point in building envelope. Together, these features ensured walls remained dry even during prolonged storms. The 250 buildings in southern England preserving 700-year-old thatched base coats weren't exceptional. They represent normal medieval construction, structures built to last, maintained consistently, designed around principles that worked. No tar was necessary because medieval builders understood that waterproofing emerged from proper pitch, correct overlapping, adequate ventilation, and breathability. We gained convenience when we developed synthetic roofing materials. Modern asphalt shingles install quickly and cost less than traditional alternatives. These are genuine advantages that make quality shelter accessible to more people. But we lost something too. We lost understanding that waterproofing comes from geometry and physics rather than chemical barriers. We lost techniques that created roofs lasting centuries rather than decades. The medieval approach to waterproofing, whether thatch, tile, slate, or lead, prioritized working with materials' natural properties rather than trying to overpower them. Thatch was allowed to breathe and move. Tiles were overlapped but not sealed. Slate relied on gravity and smoothness. Lead flexed with temperature changes. Each material was used according to its nature, resulting in roofs that accommodated rather than fought inevitable movement and moisture. This philosophy remains valid. Modern green building movements rediscover breathability's importance, using permeable materials that allow moisture to escape rather than trapping it behind vapor barriers. Heritage conservation validates traditional techniques, finding that period-appropriate repairs outlast modern interventions. The principles medieval builders employed, steep pitch, generous overlap, proper ventilation, material-appropriate installation, work as well now as they did 7 centuries ago. The 7-foot-thick thatch accumulations aren't failures of medieval maintenance. They're evidence of sophisticated understanding that adding layers was more effective than stripping to bare structure. The centuries-old slate roofs, still weather-tight, prove that proper installation creates permanence. The surviving lead work demonstrates that material selected for properties and installed with skill can function indefinitely. Medieval people built waterproof roofs without tar because they understood something we've partially forgotten. Water follows predictable physical laws. Channel it efficiently, prevent it from accumulating, allow vapor to escape, and you create weatherproofing that requires no synthetic barriers. The materials may have changed, but the physics remains constant. That's knowledge worth recovering, even if we never again hand-split slate or hand-thatch roofs with water reed.